All right, I think we are live. So last time we implemented let in the interpreter. And this week we have to parse, loop, and recur. And one thing I forgot to do last week was to extend our data structures to show how we're gonna do loop and recur in terms of the parse tree. But so we have to do that now. So now we have two new types of expressions, one of them being loop and the other one being recur. And if you look at how loop and recur are defined, let and loop are defined in the grammar is they are exactly the same grammar-wise, except that one says let and the other says loop. So we can actually reuse our let part in this union for loop also, because really all we have to do is store a number of bindings and a body. So we're going to call this let loop, and we're going to get errors if we don't change it. But then we have recur here, and recur takes the form of the keyword recur, which we're not going to save in our syntax tree, but then we have one or more arguments. So what we're going to do is we're going to need another one of these, and I'm going to call it recur. And this is going to be very similar to this one in that we're going to save the number of arguments that we have. And each argument is a pointer to an expression. Right, so it's essentially an array of expressions. And we already implemented this dynamic array thing last time, which we can reuse for this stuff. I forgot how it works, but we're going to figure it out because I wrote it myself, and it wasn't that complicated. So I said last time that we have an additional problem, and we're going to see how that turns out. Namely, that when we are parsing a recur, or when we're parsing the arguments, we need to look ahead to see whether a new argument begins or the argument list has ended, basically. And if the argument list has ended, we can't just parse the next, we can't just consume the next token, because we're in a recursive descent parser, and whoever called us is going to want to consume that token. So we'll have to implement look ahead, but let us first implement as much as we can, and then we'll see how to change that. So the easy part first. The easy part is let's look at let first. So we have these three occurrences: let loop, let loop here. Now here's the thing. This whole thing parses the let, right? But with the exception of the starting token, it also parses the loop. So we're just going to reuse this case to parse both of them. And I'm going to update, no, wait, assignments. I'm going to update this thing here. This will parse both cases. And then we have this additional case. That means that this also handles token loop. And as far as I know, the only difference here is that we need to make it an expression loop instead of let if it was a loop. So one thing, do I ever use, yes, I do reuse T. The one thing that I should do maybe is, what is the type that I've defined? So I have the expert type T, right? So I'm gonna make expert type T, expert type equals, if the token dot type is a let token, then it's an expert let, otherwise it's an expert loop. So I have to close the window. There we go. And now instead of putting this in, I use just expert type. Understood?
Mm-hmm.
Okay, so that was easy. Now on to the recur. Case token recur. Let's look at how we use this dynamic array. So we have a dynamic array that we initialize, and then we just append a pointer. And then how do we iterate? We get the nth. Okay, we're gonna do another thing so that we can just get the raw array out of it. We could already do that. I'm just gonna write an accessor function, but whatever, that's not the difficult part. So we've consumed the token recur, and now we just read one argument. So arguments are defined like such. This is an argument. So we know there's at least one argument, right? So I can just say, what is it? Expect token. I know I can expect an open paren, right? That's how an argument starts. And I can read an expression, which is the argument here. And then I can expect a close paren. Parse expression, expect token, close paren. Right, so now I'm after the first token. But this thing is notation for 0 or more arguments. And an argument starts with an open paren. Now, the grammar is structured in such a way, and you can convince yourself by thinking through what can come after what. But I'm just gonna state it out right now, and we're not gonna walk through it. But the grammar is structured in such a way that if an open paren comes, it must be an argument. There is no other way for an open paren to mean anything other than another argument. Our problem is now, is the next token an open paren? If yes, we parse another argument. If no, we don't touch the token and we return. So it would be nice if we had, actually, we could just write a loop. If we could just say while look ahead of context is token open paren. Right, that would be really, really nice. So basically, we have to implement the look ahead. So right now, the way our scanner works is that we have this function scan defined over here in the scanner directly, and it scans one token and returns it. And we use it a few times here. But we want to have a layer in between where we buffer one token ahead of time, and which is the look ahead, which you can look at any number of times. But then if you actually scan, it gives you the look ahead token and it gets the next look ahead token. So we're gonna actually make a new function that we're gonna call consume, which is gonna take a context and which essentially forms the function that scan has now. So all the calls to scan will now be calls to consume. And luckily, there's not that many. And now we have to store the look ahead token, which we have to initialize at some point. And then we also have a function look ahead, which is very simple because it only returns the look ahead token. Actually, why don't I just call this look ahead and forget about this? Oh, but then I need to, yeah, whatever, I'm lazy. Look ahead.type. So token T. So what consume does is it will return the look ahead, and it will scan the next token and overwrite what's in the look ahead, right? So we have to remember what the look ahead was. Then we say look ahead equals scan of context, and then we return the result. Does that make sense?
So we just say that the look ahead is the result from the next token we get.
Yeah.
Basically.
So we basically just buffer one token, right? It's a queue of size 1. But now the stupid thing is that we need to initialize the look ahead. So we're gonna make another function, which how did we do this for the scanner? We called it scan init. It returns a bool. In this case, I don't think we really need to return anything. We're just kind of parser init. And it takes a context. And what does it do?
So it just inits initializes the look ahead.
How does it do that?
By scanning the next token?
Yeah, by scanning the first token, basically. Assuming, that the function is the first one that's been called.
Mm-hmm.
So we just put that in here. And then obviously we need to call it. And when do we need to call it?
When parsing. Wait.
Here in main, where? Before scanning it? After scanning it?
Well, after, obviously, right?
And I think that should work.
Maybe. Doesn't look right.
It doesn't look right?
I don't know.
Does it look too easy?
It looks too easy, yeah.
Yeah, okay. It looks easy. I still don't know why it shouldn't work, but we'll see. We'll see soon enough.
Okay.
So now we still need our dynamic array, right?
Yeah.
Here we have the dynamic array. And what we actually do is we append this here. So we say dynamic array append the array. The parsed expression will be appended to the array. And now once the look ahead is not the open paren anymore, we're done, and we allocate the expr recur expression. And what we put in there is, let's look back to how we defined it, recur here. We need to put in n into expr.v.recur.n equals dynar underscore length, like so. Dynar, yeah, length. And now this recur dot, where were we? Args. Now let's look at the dynamic array. Yes. So the dynamic array, this here is already the array that we need. Except it might be a little bit larger, but that doesn't matter really, because we're only looking at the first n. So I'm just gonna call it static inline void ** dynar data rt turn. This is inconsistent. And it just returns the data. Now, of course, note, don't use the dynar after passing this data. Like you're basically taking the internal data array of the dynamic array. But at that point, don't use the dynamic array anymore, because it might do stuff with it. In our implementation, it doesn't. Like the only thing that can happen is that it will append stuff, but you know, still, it's not good practice. So this is the data, and that's pretty much it. Now what we need to do is we need to print stuff, namely case expr loop print, namely if expr, is it type expr type equals expr let, then it's let, otherwise it's loop. So that's easy. Not so easy part is case expr recur. I should put this up there. I mean, it's still easy. Actually, how did I put that in the assignment? Recur. So it just prints recur. Recur. And then on each following line, so that means that we go through the arguments expr v recur n. And also, by the way, I need to adjust this because this is now called let loop. And in these here, we have to print our indentation ourselves. No, we just can use print expr v recur args of I indent +1. Break. That's recur.
Do we have to print a indentation for recur too?
No, the This indentation is always printed here.
Oh, okay, yeah.
Okay. So first of all, we should check that it still works on stuff that we did before. No. Member reference is a pointer. Oh, yes, of course. Incompatible types, yes. So this is supposed to be an expertise ***. Okay. Where is this? Oh, this is the interpreter, yes. Still needs to let loop. 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 Let loop. Okay. All right. So let's actually go back. No, let's not go back. So right now we have the parser. So just to test, it still works in the parser. We're going to give it that. Oh, that's it. Okay. So the parser still works on the old stuff. Let's try the interpreter. And let's make sure that it works for interpreter 1.7. Okay. Let's maybe also try 1.5. Okay. And 1.3, why not? Okay, all of that works. Maybe I should write a script for that. So now let's go to the parser again, and let's now we need to write our own test cases for that. So let's go into tests and mkdir parser. What is it? 1.8. Yep. First, let's take the test from cat to looprecur1.sl, and let's just call the parser on this, and let's see what happens. So, oh, I actually know what it's supposed to look like. So it actually does look like this. So that's correct. Looprecur1.out. Now let's try a more difficult one. This one. This is, we still don't, do we have any nested loops? There's no nested loops here. Well, whatever, the parsing is easy, interpreting them is harder. But we should still have nested loop tests for the interpreter, but whatever. Let's call this, I don't know, let's call it looprecur2. And let's see what the parser says. So it doesn't crash. Let's see what it does. Loop A is 100, B is 0, if A equals 0, then B, else, recur, A plus minus 1. Looks good, right?
Fine to me.
And is this the same one? Oh no, this is factorial, nice. I mean, it's almost the same one. Let's put this one in too.
That's already for the interpreter, right?
Yeah. But it still has to parse.
Sure.
If loop does L. So it does. If loop does L. If 1, then 1, else loop x equals 1 in recur x. Good. And now just to make super sure, where were we? Parser 1.8. What?
I think you're in the wrong directory, right?
Oh, where did I put it in?
It's all in test,
Uh,
not 1.8.
oh, yeah. Well, that was stupid. Parser 1.8. Good. That was it. So it did look simple, and it was simple, but it still works. Not everything has to be complicated.
Good to know.
Because really all it is a queue of length 1 that we've inserted between the scanner and the parser, right? It like that should not be complicated.
Yeah.
Okay. So the next one, this is a little bit more involved because it doesn't fit directly with the recursive interpreter in the following sense. If you interpret this loop, you recur into another invocation of your interpreter to interpret the if. And then you recur into another invocation of your interpreter to interpret the recur. But now the problem is, if you use another recursive invocation of your interpreter to do the recur, you will use stack space that is proportional to the number of loop iterations, right? So basically, if this loop runs for 100 iterations, then you will have like 300 calls to your interpret function on the stack, on the whatever programming language you're using, on the C stack in my case. Does that make sense?
Yeah.
Which means that your memory stack is just memory too, right? But we are not for a loop. We're not supposed to use memory for loop iterations. Just for a naked loop iteration that shouldn't use any memory. So we can't do it that way. We need to find some way of, when a recur happens, to go back essentially in the stack of our interpreter, in our invocation stack, to where we interpreted the loop, and then to redo the loop with the new values. And you'll have to figure out why. Or you'll have to figure out how. I just told you why. Depending on which programming language you're using, there's probably at least 2 different ways. In most programming languages. and and we'll see how to do it in C next week. Does that sound good?
Sweet. Yeah.
All right then. Have fun with the interpreter.
Thank you very much. You too.
Bye.
Bye.